Good evening, everyone, and welcome to the Amateur Radio General Class, session number 11. So during the previous session, we had a look at the concepts of heterodyning as well as image response. We talked about what is intermodulation, and we also discussed deviation and multipliers. We also talked about the bandwidth as it relates to FM signals. We also discussed duty cycle, what symbol rate was. We also talked a bit about noise and the use of filters. Then we spoke about a couple of digital modes such as PSK31, RTTY, RTTY. We also spoke about WSPR, the FT8 mode. Then we went a bit into the packet constructs such as headers. Then we talked about what ARQ and NAK, as well as the concept of FEC. Then we wrapped up with waterfall display and over modulation. So for this evening, the agenda will be, we'll start off with talking about 2.4 gigahertz, mesh networks. Then we move into digital voice modes such as DMR, D-Star, and System Fusion. We'll also discuss what characteristic impedance is, coaxial cable, and then we'll talk about, in respect of Feedlines, mismatch and reflection. Also, the concept again of standing wave ratio or SWR. We'll talk about matching networks and antenna tuners, as well as transmission line loss as it relates to length, frequency, and SWR. And we'll also discuss parallel transmission lines, half-wave dipoles, and then we'll also discuss the concept of feed point impedance, and then we will end with ground reflection losses. Okay, so for anyone on YouTube that's seeing this session for the first time, there is a previous level to the course. We are presently doing the general class, which is level 2, but there's a previous level called the technician class. On your screen are the links to take that course. It's an on-demand course as well as all of the material. So just in case you happen upon this on YouTube or any of the other social media sites, this is the level 2 course, also known as the general class. All right, so this is where we are in respect of our curriculum. We are making pretty good progress. We will wrap up the signals and emissions today, just a couple of concepts, and then we'll move straight into antennas and feed lines. Just a reminder of the links to take the practice exams. Our usual slide on Zello and interacting with React. Just a reminder for where you can get all of the recordings as well as the documentation, including the slide deck that we are circulating. So these two links in yellow, important to the course. The book that we're using is the No Nonsense General Class License Study Guide. And of course, there are several other recommended texts. Of course, all are optional, but we highly recommend that students avail themselves of the material if they can. We had no questions outstanding from the last session. Right, so we begin the technical topics for this evening. So the first one would be the concept of shared spectrum and specifically the frequency band 2.4 gigahertz. So some of us may already be familiar with the 2.4 gigahertz band. So for example, Wi-Fi or one of the Wi-Fi bands operates on the 2.4 gigahertz band. It is also known as the industrial, scientific, and medical band, 2.4 gigahertz. So it is used by other services in a shared fashion. So the spectrum in the 2.4 gigahertz band is shared with several other services. Some people call it the unlicensed band. And the reason they call it that sometimes is because you usually don't need to get a specific license. Sometimes there's a registration process, like in Trinidad and Tobago, you have to go through a process to register some of these devices, and some of them are class licensed. So you may already know about 2.4 gigahertz if you didn't know it in respect of Wi-Fi, because there are other bands that Wi-Fi uses now, such as 5 gigahertz, but 2.4 is typical. But also, did you know that your microwave oven, also the emissions inside of that microwave oven is also in that 2.4 gigahertz range? That may also explain, some persons may notice that, if you have a microwave oven that's close by, especially if it has a leak, when you set that microwave off, no, all of a sudden, if you were using the 2.4 gigahertz Wi-Fi band, all of a sudden you drop off, just for the time that the microwave is operating, and you're wondering how come. You're thinking maybe it has to do with the voltage or something like that, but no, it's not. It's the microwave, that magneto is actually generating a frequency or frequencies in the 2.4 gigahertz range. So that's why we say that this part of the spectrum is in fact shared spectrum, 2.4 gigahertz, and it's also associated with Wi-Fi. Now, you'd probably want to know, why are we dealing with this, or why we have a specific treatment of that 2.4 gigahertz band for amateur radio, if it's a Wi-Fi band or microwave, or it's an ISM, as we say, industrial, scientific, and medical. Well, hams being what we are, we tend to repurpose things. We tend to take commercial gear. We also tend to hack stuff. So it is actually not entirely unusual for us to take commercial Wi-Fi gear in the 2.4 megahertz, 2.4 gigahertz, I say again, band, use custom firmware, or some people will say hacked firmware. And because our license allows us a certain power level as well as specific of the spectrum, we are able to use that Wi-Fi equipment, repurpose it, flash it with custom firmware, and you run higher power levels, as well as we have a little more spectrum beyond what, let's say, the Wi-Fi band typically allows. So that's a privilege as an amateur radio operator when you get your license. It's a responsibility, but you also have a privilege to do things that a regular member of the public who does not have a license is able to do, because you're trained, you're discerning, you understand safety, you understand what you can and cannot do. That's why you're taking exams as well. So that coming with that is some privileges, and that's one of the privileges that as an amateur radio operator we have to use that part of the spectrum, that ISM spectrum, 2.4 gigahertz, and some additional frequencies adjacently to it, and use that to create our own Wi-Fi networks. But not just any regular Wi-Fi network. We also create a mesh Wi-Fi network. And what we mean by mesh, if you look on your screen here, you will see that we have a matrix here. You have different nodes. These are Wi-Fi nodes around the town. And each node, Wi-Fi communicates to the other node, and it communicates to another node. And therefore, you'll see that you have multiple routes for a packet or traffic to get from one node to another. And if one of the nodes were to go down, it can reroute usually via another leg. So this is what we mean by a mesh network, sort of many to many. So this router here can see this router, it can see this router, it can also see this one as well as this one. So that's what we mean by a mesh network. And the software takes care of the routing for you. And you can also connect this to the internet and have internet routed through this network as well for licensed amateur radio operators, right? But it's a pretty resilient form of communication, uses regular commercial off-the-shelf equipment. These are on your screen here, the older Linksys routers, but certainly the Ubiquity line, as well as a couple other manufacturers, they allow flashing of the operating system on these devices. Sometimes we say hacking them, right? But it's really flashing or reflashing using software or firmware that is developed by hams who are so capable, taking into account the license, the flexibility of the amateur radio license that allows us to use this 2.4 gigahertz spectrum, higher power levels, as well as additional frequencies beyond what the public is allowed. So we create mesh networks, and they also tend to be relatively high speed compared to the other speeds that's available on amateur radio generally. So we utilize this band in such a way that we can create mesh networks, and sometimes we can cover pretty wide or large geographic areas. And such networks can actually come in quite handy for disasters and emergencies, where we can fire up a network and send information, patch traffic about injuries where medical attention is needed, or any sorts of resources in an incident command system, right? So not only are we using radios, regular traditional radios, handheld, mobile, base stations, and HF and VHF and so on, but we are also using that part of the UHF spectrum in the 2.4 gigahertz range, right? So we do have an exam question coming up. Here we have just exploded the view a little bit to see, again, this is an example of a mesh network, right? So whereas this router here cannot see this router because of this hill, it can certainly communicate with the router through this intermediary router. And that's what we mean by a mesh network. So that if one of these nodes were to fail, the packet or the internet or the traffic can certainly still reach to other nodes via an alternate route, right? So that's the other connotation of a mesh network. And there are two that are pretty popular. One of them, used to be very popular some years ago. That's Hamnet, Broadband Hamnet, also called HSMM, Mesh Network Multimedia, and AREDN. That's the other network. And of course, there are a couple others as well that's available, but these are the popular ones. But the concept that you need to be aware for the exam is that mesh networks imply that when you have a network like this, if one of these nodes were to fail, you have an alternate route, or they can go through or take alternate routes through other nodes, and each one of these are considered a node to get to its destination. And this is an exam question in yellow on your screen, right? Okay, so let's talk about digital modes. So we have already discussed digital modes in the technician class level. We have also discussed it already in the general class level. But what is a digital mode? We did say a digital mode is using ones and zeros to communicate. And we did say that digital modes, especially like an HF, is using a computer to communicate instead of voice. So this is the general digital modes that we speak of, right? So just a reminder slide, but we're now coming to the concept of digital voice modes. So as before we said, a digital mode is you connect a computer to your radio, usually using some sort of interface device. When we speak of digital voice modes, we are actually speaking, except that when we speak into the microphone of a radio, something called a codec is used to translate our analog voice into digital. So that is exactly what is going on. And we have a couple of bits of graphics on your screen to illustrate that process, right? But what is important for the exam is that there are a couple of digital voice modes that we need to be aware of. And all of them will take our analog voice and encode it using something called a codec. And that encoding, it encodes it into a digital mode for transmission digitally over the air, or sometimes even over other means such as the internet, right? So the digital voice modes that are quite popular today, we have a few of them on your screen, such as DMR, D-Star, and System Fusion. So this is what you'll get in the exam. They'll ask you, what are examples of digital voice modes? These are the examples. And we have, given us some extra information as to what DMR means, what D-Star stands for, and even System Fusion, the actual modulation scheme. And there's another one called P25 or Project 25. Right, so these are some of the logos or the symbols associated with these modes. So when you see DMR, okay, that means DMR. When you see this symbol here, D-Star, it means D-Star. When you see System Fusion, that means C4FM, and so on. And these are some examples of digital radios. And we have a little block diagram that shows how a digital mode operates as far as digital voice. So we need to be familiar with digital voice modes, DMR, D-Star, System Fusion, and all of them take our voice, digitize them, and put them on the air, either via RF radio frequency or sometimes over the internet. All right, so a little bit of extra information. We covered some of this before in the technician class, but just so that you're aware. So when we say that we can use the internet, you probably say, wait a minute, is that amateur radio? Well, it certainly is. We can use these devices called hotspots. And what a hotspot will do is take our RF or radio frequency from our radio. It's transmitting radio frequency into the hotspot, also via radio frequency, of course, but it will use the hotspot, digitize everything, and send it over the internet, right? So this is what a hotspot may look like. Just to also give you an idea, these are other examples of hotspots. So this is how we bring our radio frequency, our digital voice onto the internet. And some of these hotspots are multi-mode. They can do all of the modes, DMR plus D-Star plus C4FM, one at a time usually, but it can do all of them And you can take advantage of these devices. They're quite flexible to do all of these digital voice modes when you get your license. You can use one radio and you can do something that's called transcoding. So you could be speaking DMR from your radio to a hotspot, and the hotspot can send it out via a system fusion network, for instance, right? Okay. Right, so this is just a slide that gives a bit of detail on what DMR is, so you can read this on your own time. A slide that talks a bit more about DMR and talk groups and what a code plug is and so on. So you can read that on your own time. Also, a little bit of information about D-Star and what a D-Star radio, the settings on a D-Star radio would look like. So if you have a D-Star, you have some settings that you have to put in for D-Star to work. So you have to configure your radio. So just give a little idea as to what it looks like practically when you become a licensed ham and you have a D-Star radio. This is what you'll be seeing. None of these are, of course, are exam questions in detail, but just to give you a little bit of idea when we talk about DMR, D-Star, and then system fusion. This is what a fusion radio may look like, a digital mode, right? So you see the digital mode that is enabled here, right? So just some extra information. And folks, that wraps up that topic. So we now go on to the next topic in our syllabus. All right. So we're now talking about feed lines. Now the question is, what is a feed line? Sometimes also called a transmission line. And that is simply the cable that we will use to connect our radio to our antenna. Right? So we must connect the radio to the antenna somehow. And that cable or that line is called a feed line, or sometimes called a transmission line. Of course, there are many types, and we'll come to talking about a couple of them in a little bit, right? So just bear in mind, anytime we say feed line or transmission line, that is the cable that we use to connect between our radio or transceiver and whatever antenna we are using, right? So we need to be aware of a concept for the exam called characteristic impedance, right? The impedance, so the transmission line, and on your screen here is an example of one type of transmission line. It's a parallel conductor, and we'll come to another slide that will show that there are different types of this parallel conductor line, right? But for the purpose of this discussion here, we have just explored the view of one of these types of feed lines, right? It's called the parallel conductor transmission line, and we have other names that we'll come to in a little while, but we just for now call it the parallel conductor. Why do we call it parallel conductor? Well, this is one of the conductors here, and this is the other conductor, and they are roughly parallel. This insulator here, also sometimes called a separator, is what holds these physically at a fixed distance apart, right? So this is copper line usually, or copper wire, another copper wire, and they are parallel. So hence why we sometimes call them the parallel conductor line. And again, we'll come to a couple of the terms that we will use, such as ladder line and twin ax, different types of terms that we will use to describe this parallel conductor line. But we need to be aware that for all transmission lines, they carry what is called an impedance or characteristic impedance. And for the purpose of their exam, you need to know for this type of transmission line or for this type of feed line that is called parallel conductor line, the characteristic impedance is calculated by knowing two properties of this transmission line. The first one is how far away these two lines are, or the distance between the conductors. So this distance here is one of the parameters that determines the characteristic impedance. In other words, if you move these two wires or these two lines closer together, that changes the characteristic impedance, right? Similar to, remember when we were talking about capacitors, for example, move them closer, move them further apart, and it affects the capacitance, right? So in a similar way, when these two lines are spread further apart by these insulators, or they may be closer together because you have a shorter insulator, that will affect or change the characteristic impedance of this type of transmission line. The other parameter that we need to know for the exam that affects the characteristic impedance is the radius of the conductor, right? So these are conductors, and they will have a radius or radii. And those two are what you need to know for the exam. But we've just put a bit of extra information here for you. We have shown, okay, there's a cross section of the two conductors, right? They're roughly circular, right? And each one has a diameter. And of course, there's also a distance between the two parallel conductors, right? So this is a cross-sectional view looking into the conductor. And there's the formula for characteristic impedance. It's equal to this, right? Don't need to learn this for the exam, but we're just giving extra information that you can see that the distance, which is this d here, between the two conductors, as well as the radius, which is small d, is or are some of the parameters that's used in calculating characteristic impedance. And you may remember we dealt with impedance before. We talked about resistance, we talked about reactance, and so on. And we may remember that Z is the symbol for impedance. And this little C here just means characteristic, right? So the characteristic impedance is equal to this little fancy formula here, of which part of it includes the distance between the conductors as well as the radius of the conductor. And this is an exam question. So hopefully putting this out here diagrammatically as well as picturesque, you hopefully get an appreciation of what is being asked and what the answers are to this particular question. Characteristic impedance affected by or determined by the distance between the center of the conductors and the radius of the conductors. That's all you really need to know for the exam. All of this rest will be extra information that will hopefully help us understand. All right, so we just dealt with one type of feed line, right? Parallel, this one here, the parallel conductor, right? So you have two conductors that are parallel. We now come to coaxial cable, or sometimes abbreviated coax. And this type of cable on your screen here, we have stripped out some of the layers here so we can see inside of what it looks like. But this is pretty much typical of the type of transmission line that amateur radio operators will use. It's called coax. And there are different types, different design of coaxial cables, right? Some are thicker, some are thinner, some are more flexible, some are more inflexible, some have more losses per foot, less loss per foot. And each of them will have a particular characteristic about them, right? But what we need to know for the exam is that this here is called coaxial cable. And we typically have a characteristic impedance of 50 ohms, right? So this is in fact what amateur radio operators, once you become a licensed AM, you'll find yourself, once you're connecting radios or transceivers to antennas, you will find yourself using quite a lot of coaxial cables, right? So here it is, coax. And why it's 50 ohms? Well, typically we are trying to match our transceiver that also has an output impedance of 50 ohms. So we tend to use coaxial cable that's 50 ohms. Now, some antennas will be close to 50 ohms and some are not, right? So there's where the whole idea of matching and mismatching may come in. But the point about it is that coaxial cable, the characteristic impedance is 50 ohms. That's 50 ohms. So you just mentioned sometimes you could have a mismatch between the radio output impedance, the transmission line, and the antenna feed point impedance, right? So that's what you are trying to do. And we did say previously in the technician class, we talked a bit about it already in the general class, that hams are matchmakers. We are also always trying to make a match. But make a match of what? Well, impedance, right? Or impedances, right? We are trying to match the output impedance of our transceiver. This is our transceiver or our radio that has a transmitter, and the way designed in such a way that the output impedance is 50 ohms. So therefore we tend to use a 50 ohm transmission line or 50 ohm feed line. And we are hoping that the antenna itself, the feed point of this antenna, also has a 50 ohm feed point. It's not always so. Sometimes it's so, or sometimes we can make it so. Sometimes we have to help it along. But that's what we are trying to match. We are trying to make sure the characteristic output impedance of this radio matches the characteristic impedance of the transmission line and the characteristic antenna feed point impedance as well. We're trying to have all of these as 50 ohms. But why are we doing that? Why do we want it to be 50 ohms, 50 ohms, 50 ohms? The reason is that we want all of the power that we transmit from our radio to go to the antenna and leave the antenna as radio waves. That's what we're trying to do. We don't want any of that to come back into the radio. And that is exactly what will happen if we don't have a proper match, or if we have a mismatch. We'll have some of this power being reflected back down the transmission line to the radio. And that could cause the circuitry to be detuned here and cause heat, and you can even damage, could lead to potential damage of your equipment as well, right? So as hams, we are matchmakers, and we are trying to make sure that we maximize the output power from this transceiver or this radio transmitter, so that all of the signal goes, or as much of the signal as possible, the most of the signal goes to the antenna, because that's what we're trying to achieve, the maximum amount of efficiency. And that's why impedance matching is important. We are trying to match this transmitter output impedance with the characteristic impedance of the coax cable, or the transmission line, or the feed line, with the antenna feed point. So that's what we are trying to do. If it's not mismatched, or rather if it's mismatched or it is not matched, then we have a reflected power coming back down, and it creates what is called standing waves. We do not want standing waves, right? We want all of our power to go to our antenna, right? So let's talk a bit about standing waves and standing wave ratio. So when there's a mismatch between the feed line and the antenna feed point, so we have our feed line here coming from our transceiver, and we have our antenna here, and the feed point is where the transmission line connects to the antenna. If there is a difference in the impedance, so let's say the transmission line is 50 ohms, right? And let's say our antenna is 72 ohms or something like that, then there's a mismatch, right? So once there's a difference in the impedance, we have a mismatch. And that mismatch, to measure it, we call that voltage standing wave ratio, or sometimes simply standing wave ratio, abbreviated as SWR. And as hams, we'll be ad nauseum talking about our SWR. We are very interested to know, what is our SWR? How can we bring down our SWR? How can we get a perfect match of our SWR? But essentially, the SWR is the ratio of these two impedances, right? And when that impedance matches, that is, the 50 ohm transmission line or feed line is connected to a 50 ohm antenna, the feed point of the antenna is 50 ohms, we then get what we'll call a perfect SWR, or as close as perfect as you can get, which is 1-to-1. So if you have a 50 ohm feed line and a 50 ohm antenna feed point, you have a 1-to-1 ratio. And that is very important as amateur radio operators. Why? Because we are matchmakers when we're trying to make that match the transmission line characteristic impedance with the antenna feed point impedance. Now, what can we do to prevent standing waves, or to have a high SWR? That's a question that we ask ourselves, and it is simple. Well, simple to talk about. We simply want to match this antenna feed point to that of the characteristic impedance of the transmission line. And an exam question, right? We're trying to match this feed point here of the antenna. That's the antenna feed point here. That's why we circle it in yellow, along with the characteristic impedance of this transmission line. Again, this transmission line is what connects our transceiver, as in this diagram here, you have a transceiver or transmitter. You have our transmission line or feed line to the antenna. So we are actually trying to match these two impedances. And if we are able to do that, we will prevent a high SWR, or prevent standing waves from being present, which we are trying to really assiduously avoid. So let's do a calculation, which will hopefully help us follow along a bit more. So we need to do a couple calculations for the exam, right? And we take it directly from the exam question. So SWR, how do we calculate SWR? Well, a simple way is to just have the ratio of the impedances of the antenna and the transmission line. So we have on your screen here the little formula. SWR is the ratio of the load impedance to the feed line impedance. So Z again is impedance, and we have a little subscript here, load, and a subscript feed line. So read this as standing wave ratio is calculated by, or is equal to, the impedance of the load. And in this case here, our load is our antenna. Whatever the end, you could have a dummy load, you can have an antenna, right? So that's the load. 2, or the ratio to the impedance of the feed line. So that's all this fancy formula is telling us here. So we just need to put the impedance of the load, put the colon, and then put the impedance of the feed line, and that will give us our SWR. So let's try an example. And this is an exam question, right? And after we complete this, we will then take a short break, right? Question is, what standing wave ratio, or SWR, results from connecting a 50 ohm feed line to a 200 ohm resistive load? So let's dissect this question a little bit. What are they asking us? What standing wave ratio? So they're asking us for SWR, so we need to end up with an answer that is a ratio. 2 to 1, 3 to 1, 4 to 1, that's a ratio, right? So they're asking us to calculate a ratio. But using what? Say it's connecting a 50 ohm feed line. So remember, feed line is the same as the transmission line. That's the line that we use to connect our radio to our antenna. So we have a 50 ohm, that's a characteristic impedance of the feed line, 50 ohm transmission line or 50 ohm feed line. To what? We are connecting the radio to a 200 ohm resistive load. And we put just here antenna because this could easily be an antenna. So when we say the load, could be an antenna, for example, right? But they're telling us it's a 200 ohm resistive load, right? Okay, so we do use this little formula here, trusty formula for SWR. We put, first of all, the impedance of the load. Did they give us that? Yes, it's 200. So we put 200, and then we use the colon to show the ratio. 200 to what? Well, they gave us the other one, which is the feed line impedance, as 50 ohms. So it's 200 to 50. But we don't really want to give a ratio of 200 to 50. It sounds kind of awkward. We want it to be a little simpler than that. So what we can do here, just examining this, we can divide both sides of this ratio by 50 to bring this right-hand side down to 1. So you'll get something to 1. So if we divide 50 by 50, we get 1. That's on the right-hand side. So that's how we get this 1 here. And when we divide 200 by 50, we'll get 4. So that's our ratio, 4 to 1 ratio. And that's the answer for this question, this SWR calculation. It was nice. Let's do it twice. So there's another question, very similar indeed. What standing wave ratio, or SWR, results from connecting a 50 ohm feed line to a load having 10 ohm resistive load? All right. So we should see a pattern here. These two questions are very similar. Dissecting them or dissecting it, we see that they're asking us to calculate an SWR or standing wave ratio. So therefore, we know it's going to be something to 1, or there's a ratio that we're looking for. And we're using our trusty SWR formula, right? We need to get the impedance of the load. They did give us that. Yes, they did. They told us what it is, right? It's 50 ohms, right? And then the feed line, what is it? It's 10 ohms. So therefore, we put 50 to 1 and we divide by 10. So we get 5 to 1, which is the answer. So folks, let's take a break at this point and we'll come back and do the rest of the technical topics. So please have a little break, probably get some water, take a bathroom break, take a stretch, and we'll be back in 2 minutes time. Okay, everyone, welcome back. Good evening there, Adish. Just all as well. All right, let's deal with one question I'm seeing coming up. Jason asks, what happens if the transmitter feed line disconnects during a transmission? Can it damage the transmitter? That's an excellent question. So the answer will be, it depends. So if you are running high power, there's a very good chance that it can, because if you're running low power, it depends on the length of transmission. If you transmit continuously for several minutes at a time, it probably will get to the point. If it's very short or brief transmission, it also depends on the duty cycle. That's why sometimes, in some cases, transmitters will have a device called a circulator that may take into account, let's say, if the antenna gets damaged, or maybe the feed line going up to the tower gets disconnected or severed or something like that, right? So yes, it is possible for damage to occur, but there are also solutions that you can apply. You would want to make sure that you have very good tight connections as well, so that the connections cannot easily become loose. So I would say the answer really depends, Jason, but I would go with yes, it is entirely possible, and you would want to take every precaution to avoid it from happening. And if you think it is likely for some reason, then you probably would not want to run, at 100% duty cycle or maximum power. You may want to be conservative. So if it does occur, damage will be less likely. I mean, transceivers are built with some level of robustness, so it may not immediately damage, but a lot has to do with, what the operating conditions are at the point in time. So really, I think the best answer I can give, it depends, but certainly it is possible. All right, so let's move on and continue where we left off. All right, so we did say that, as hams, we are matchmakers, right? And going along the line, the question that Jason just asked there, the first bullet point we have here, say yes, damage can result if a transmitter output is connected to an impedance that is not 50 ohms. So if you disconnect your transmission line, well, that impedance is certainly not 50 ohms, right? So whether damage will occur or not, it really depends on a number of factors, right? But certainly, any impedance that is not 50 ohms at the transmitter, because transmitters are designed to have an output impedance of 50 ohms. Anything that's not 50 ohms, it's not seeing 50 ohms, is the highest WR, right, at the end of the day. So you're looking to match, as hams, we are trying to match that 50 ohms. So what if it is not 50 ohms? What if, for example, you have a transmitter coming into this 50 ohm transmission line, and you have something other than 50 ohms, maybe 72 ohms or 46 ohms, or whatever it is here at the antenna. Are you powerless? Certainly not. So as hams, we are matchmakers, we find a solution. We can put in a matching network, or sometimes call a antenna tuner, right? That's a device that we can put in circuit that will allow the transmitter to see or appear to see 50 ohms by adjusting. And those antenna tuners tend to have coils and capacitors, right? Remember, we discussed the whole idea of matching networks, pi networks, LC networks, and so on to match. So we can use a matching network of some kind, or sometimes more commonly known as an antenna tuner. And we'll come to a next slide up, showing what an antenna tuner might physically look like, where we place it, and what it does. And then we'll also discuss another exam question in relation to antenna tuners and matching transformers or matching networks, right? So what those devices do when we put them is it allows the radio or the transmitter to think it is seeing 50 ohms. Now, the reality is that when we put something to adjust insert to make the transmitter see 50 ohms, it's not actually 50 ohms, the transmitter is just seeing it. But whatever the impedance is, remains the same. It doesn't actually change the impedance on the line, but the transmitter. So in a way, you could think about it as fooling the transmitter, right? But the transmitter will be quite happy. But quite frankly, when you use something like that, the efficiency of that, you're not maximizing the efficiency as well. It's just that it'll make the transmitter happy. So you need to be aware of that. The actual SWR remain the same. They are still standing waves, but just that with respect from the perspective of the transmitter. And we'll come to a slide that hopefully show that in a little bit, right? So hang a little bit for a visual on it. The actual SWR remains the same on the line. You have the standing, but the radio will be a lot happier, right? So if it is, for example, that the antenna feed line has an SWR of 5.1, and we put in an antenna tuner or matching network by the transmitter, and we adjust it, we turn the knobs, we turn the coil, we turn the capacitor a bit, and all of a sudden now the radio is seeing an SWR of 1:1, right? We need to know that the SWR on the feed line is still 5:1. So even though we're using a matching network or an antenna tuner to make the radio see 1:1, it actually doesn't change on the feed line itself. It still remains 5:1. If before we put the matching network or before we put the antenna tuner in circuit, it was 5:1. After we put the antenna tuner or the matching circuit in, it is still 5:1 on the actual line, but the radio will just see 1:1 when we adjust the tuning dials, right? So we'll come to a graphic to show us what it looks like. All right. All right, nice. So as promised, we have a bit more information here in terms of what we're talking about. So this is our radio, our transceiver or transmitter. This is our antenna. And then we have our feed line or transmission line. We have just inserted a matching network into the mix. It's also called an antenna tuner. And you'll notice we have some knobs here. And these knobs actually tune or turn coils and capacitors inside of there. So this one here, this knob, for example, will turn a coil. And these knobs here will turn capacitors, things like that, right? And these tuners, some of them will also have an SWR meter on the face itself, so you can see what it is. But for the exam, we need to be aware that even though we started off with an SWR of 5.1, standing wave ratio, they're standing waves, and the SWR is 5.1. Even though we put this antenna tuner into the circuit, and we tune it such that the radio is happy. The radio now sees 1:1. It says, wow, I am perfectly matched. My output impedance of my transmitter is perfectly matched with everything that goes after it. So life is good. It is actually not. What is happening, you're fooling in a way the transmitter to think it is seeing a 1:1. So it becomes very happy. It will dutifully transmit. And you wouldn't damage your radio and all of that. But the efficiency is what is affected. But the SWR is still there, the standing waves are still there, but your radio will transmit happily. All right. So this is the setup here, and we have an exploded view. This is a top view of the inside of what this looks like. So you'll notice that we have some, these are two tuning capacitors, and this is the example of the coil that we are turning, and the capacitors that we are turning as well. We are varying the area of the plates, so therefore the capacitance is changing, right? So it's L and C again, L for coil and C for capacitor, L for inductor and C for capacitor. That's a matching network consisting of coils and capacitors, right? So see how the earlier theory is helping us to understand a little bit now when we talk about the components inside of there. See practical example of when we use these components in circuits to actually achieve something, right? So this is an exam question here. One of the reasons we are using either a matching transformer or an antenna tuner or a matching network is to present the desired impedance. What is the desired impedance? 50 ohms, such that the SWR is 1:1 to the transmitter, right? So that's why we are using this matching network or tuner in circuit. And as hams, we tend to use this because quite often an antenna may not be perfectly matched. Sometimes we use a multi-band antenna. Sometimes we use a single band antenna, but we want to use it on multiple bands. And we end up using an antenna tuner. Sometimes radios will have an inbuilt antenna tuner in them, but they may not be able to tune every single impedance, right? So sometimes we need something a little more robust with larger coils and capacitors that could really tune down. Again, it works. It's fine. No issues there. But some hams will say, it's better to have an antenna that is properly matched per band instead of using antenna tuners. That's in an ideal world, I guess we can do that. But sometimes you use an antenna tuner. Right? All right. So we said that if we want to have maximum transfer of power from our transceiver or transmitter to the antenna, we need to have a SWR of 1:1. That's the ideal SWR. So if it is that for coax cable, that type of transmission line, if the SWR is greater than 1:1, what happens is that the signal will be reduced because losses increase as SWR increases, right? So we'll come to a slide that talks about that a little more, but we just need to know that the higher the SWR on your transmission coax line, the more reduction will occur as the SWR goes higher and higher, right? So SWR gives you a double whammy. It's high SWR is not a good thing. No, the reality is that you may not be able to tune the SWR down to 1:1 in all instances, right? There are practical limitations sometimes, but the whole idea is to try and reduce the SWR as much as possible. You're trying to aim for 1:1. It may not always be possible to get 1:1, but you're aiming for as low as you can go, right? All right, so again, if the transmission line that you have is a lossy transmission line, meaning that it's a poor transmission line, and remember we did say that there are different types of coaxial cables. So the lossier that coaxial cable is, the higher the SWR that you end up having, it will double whammy the loss that you get, right? So that's why sometimes you want to use a better quality coaxial cable so that the loss per foot is less. So the effects of a high SWR will not be as bad, right? So that's why as hams, we will invest a little more in good quality transmission line. And when we're investing in coaxial cable, you'll hear about LMR 400. Hams will say, all right, I'll use LMR 400 because that has a lower per foot loss. And therefore, you have a high SWR, the losses associated with a high SWR will not be as much as if you had used a lower quality coaxial cable. Let's say LMR 240 or so, you have more loss per foot if you have a high SWR. So these are the things that we need to know about as amateur radio operators so that we have optimality in our transmission. Let's move on. Okay. So we need to be aware that no matter what we do and we get a 1:1 SWR, even if we match our coaxial cable and our antenna feed point to that of our transmitter or transceiver, that's 50 ohms, even if we do a perfect match, we will still have some reduction in the signal as it goes across the transmission line. The transmission line is not perfect. It will not transfer 100% of the energy or the signal from the radio to the antenna, even if you have a 1:1 ratio or the SWR is as low as 1:1. We have signal loss or reduction in the signal. A term that we use to describe that is attenuation. And as an amateur radio operator, we need to become familiar with that term, attenuation. Attenuation simply means a reduction in the signal, right? It presents a reduction to that signal that is transmitted. When it leaves the radio, it ends up at the antenna a lower signal because of that property called attenuation, or the reduction in signal, or the signal loss. And we need to be aware for the exam, there are two questions you will get in respect of attenuation, specifically on coaxial cable and transmission lines in general. And one is that the higher the frequency of your transmission, the more the attenuation, right? So the example that I have here on your screen is that if you're in the 440 megahertz band, for all things being equal, the loss will be higher for the higher frequency compared to, let's say, if you're on the 2-meter band, 70 centimeter band or the 400 megahertz band, you have a higher loss compared to the 144 megahertz band or the 2 meter band, you will have a lower loss per foot, right? That's just how it goes with transmission line. The higher the frequency, the more loss you will get. So you need to be aware of that for the exam. Also, the longer the cable, the more loss you will experience. And as a matter of fact, we actually give a property of the particular cable, no matter what type of cable that you use, we will say that there's a line loss in dBs per 100 foot, right? So decibels per 100 feet, right? That's a property when you're looking at coaxial cable or any kind of cable. You want to know how much loss you will get per 100 feet of cable, because some cable will have less loss per 100 feet. So you want the least amount of loss as well. You don't want your signal to be wasted, to be given off as heat, for example, a cable. What you want is maximum transfer for efficiency from your radio to your antenna. Why do you want to lose signal along that transmission line? By using a poor quality transmission line. So you want to know what is the loss per 100 feet inside of there. So you will probably use the lowest loss per 100 feet that you can afford to implement. Okay. All right, we have a few more slides to go. All right. Now, because we as hams, we say, the lower the SWR, the better. SWR readings can be misleading. You'll say, but wait a minute, we said earlier that the SWR is the holy grail. As hams, we are matchmakers. We are trying to achieve the lowest possible SWR. But how am I now saying that the SWR measurements could be misleading? We need to be aware that the more lossy your feed line or transmission line is, especially when it's very lossy, if you get an SWR reading on your SWR meter, that could be misleading. It may be artificially low. As long as you have a low quality transmission line that's very lossy, you may say, but look how low my SWR is. But your SWR is not really low, It's actually quite high. But because this transmission line is so lossy, it gives you a phantom reading and it appears to be low. So just bear that in mind as an amateur radio operator. Say, wow, my SWR is low. It's not low. You're using really poor quality coaxial cable or transmission line or feed line and think your SWR is low, but it really is not. So this is an exam question, right? If you're using poor quality transmission cable with the higher transmission line loss, the more your SWR will be reading artificially low, and that's an exam question. So bear that in mind. All right. So we talked about parallel transmission lines before, right? So we're now showing on your screen a couple of different types. One we need to know about for the exam, but we're showing, again, a bit of extra information. Call them twin lead, we can call them ladder line, open feed line, but they actually mean something specific, right? And depending on how your parallel transmission line is constructed. Now, why do we call it parallel transmission line? Because the conductors are roughly parallel, right? So you have separators or inserters between the actual copper lines or the metal itself in the line, and they are parallel. So that's why we call them parallel transmission lines, right? Two wires that are parallel, but we can space them differently. And by doing so, remember we said that as we change a couple of characteristics, the diameter of the conductor as well as the distance between the centers of the conductors, we change the characteristic impedance. And we're seeing that here. We're seeing that, look at these closely spaced conductors. The characteristic impedance is 300 ohms. For this particular type of parallel transmission line that we actually refer to as ladder line, or for the exam, we're calling it window line. And if you want to know, it looks like a little window here, right? So also called ladder line because sometimes it looks like a ladder. It's 450 ohms, and that's an exam question. Ladder line or window line, the characteristic impedance is 450 ohms. And this open wire type feed line, right? So it's basically wires, and you just use some insulators and spread them apart, or spreaders they're called sometimes, insulators. It can vary between 600 and 800 ohm. You can actually construct this yourself. Right, so for the exam, we need to know the characteristic impedance for window line is 450 ohms. Exam question. All right, so this is just a bit of extra information for you. There's a type of antenna called the random wire antenna, right? And that's just a length of antenna that you connect to an antenna tuner and to your transceiver, and you tune it using the antenna tuner. So that's the random wire antenna. Not on the exam, but extra information for you. You can have a look at and read up on your own time. What we need to know about for the exam, though, is the half-wave dipole antenna. So the half-wave dipole antenna is, we had a look at it before, but we're going to get a little more in depth into it and do some calculations as well. You have your transmission line that comes to the antenna, and you have two conductors, and each one of them is quarter wavelength each, right? And together it forms a half-wave dipole antenna. It is a very common antenna that is in use. Hams use these all the time. But we need to know that the formula to calculate the length of a dipole antenna, right, and how we calculate it. And the formula is the length is equal to 468 divided by F, where L is the length of the antenna and F is the frequency. All right. So let's do an actual calculation. These are two exam questions that you will get. First one up, what is the approximate length for a half-wave dipole antenna that is cut for the 3.550 megahertz frequency? So let's dissect this question a little bit. So imagine we are, as a ham, we want to construct this half-wave dipole antenna, right? This is the diagram here. And below, it actually shows us that we have constructed the antenna and we are mounting it, right? We have a mast here and we have a tree and we have some insulators and we have our antenna that is installed. Each leg of the antenna is quarter wavelength, but we need to know how do we calculate the length of this half-wave dipole antenna. Well, we use our trusty formula, L is equal to 468 divided by 3.55. Now, bear in mind that when we use this formula, we have to use the units that we're given, right? So again, coming back to the previous slide, notice that the L is the length in feet, right? And the frequency is given in megahertz. So if you get your question in anything other than megahertz, or you want to find out in some other units other than feet, you will have to adjust, right? So this formula is valid for the length using the units of feet, and the frequency will be in megahertz. Right. So we use our trusty formula, L is equal to the 460 divided by the frequency. What is the frequency in megahertz? 3.55. So all we do is substitute for F, 3.55 in the denominator. We do a division. You can check it yourself, use a trusty calculator, and you will get approximately 132 feet. And that's the answer. So in the exam, you could try to remember the answer is 132, but better yet, remember the formula so you can calculate it. Remember, you are permitted a standard calculator in the exam, right? So once you learn the formula, you can calculate any question that you will get, right? Or you can remember the answer if you wish, but better yet, learn the formula. Because we have another question that is very similar as well. What is the approximate length for a half-wave dipole antenna that's cut for the frequency of 14 or 14.250 megahertz? Let's dissect this question. Similar to the previous one, they're asking us for the length. Length of what? An antenna. What type of antenna? Half-wave dipole antenna. But for what frequency? 14.250 megahertz. What formula do we use? Our trusty formula, L is equal to 468 divided by F. So all we have to do is substitute F for F, what they gave us, the frequency 14.250, and that's what we do in the formula. We use our trusty calculator, numerator 468, denominator for 14.250. When we plug that into our calculator, we should get 32 feet approximately, right? So again, this is what it looks like diagrammatically, and this is what it looks like if we were to actually do an installation physically. All right. All right, so a couple more slides, folks, and then we will go into our question pool. So we're going just a little bit over time this evening. All right, so this is our half-wave dipole, right? So each leg is a quarter wavelength long. Now remember we talked a bit about the feed point impedance. We talked about the transmission line characteristic impedance. We talked about the output impedance of our transceiver. But we also talked about the impedance associated with the feed point of the antenna. And the feed point of the antenna is this point here. This is where the transmission line connects to the antenna. That's the antenna feed point. And one leg of the antenna goes this way and the other leg of the antenna goes this way. All right. But there's a characteristic or there's an impedance that exists at that feed point. For a half-wave dipole, the feed point impedance is actually not 50 ohms, but somewhere in the vicinity of about 72 ohms, right? So remember we said we are trying to make antennas that the feed point is 50 ohms because we are using 50 ohm, typically 50 ohm coaxial cable, and typically our transceivers are expecting or have an output impedance of 50 ohms. Hams are matchmakers and we try to match that, right? But the reality is life is not always ideal. It's 72 ohms when we construct a dipole as is, right? But we need to be aware that if we were to move this feed point away from the center, so remember for a half-wave dipole, either leg is quarter wavelength long, but we can choose to make these legs, one of them shorter than quarter wavelength and the other one longer than quarter wavelength. So as long as the total is half wavelength, we can do that, and we call that moving the feed point. So we can shift the feed point in either direction. We can either shift it towards this end or shift it to the other end. And when we do that, if we shift the feed point from here to, let's say, about here, what we are doing is we will increase the impedance of the feed point, right? So that's what occurs. It doesn't stay the same. You would think, well, all right, it's still a half-wave dipole. But no, we have moved the feed point of the antenna from here to somewhere along the length here, either direction, right? And it will increase the impedance from what the standard impedance would be had it just been exactly at the center point. Now, the other thing is you may take a look at this diagram and say, well, wait a minute, I have a mast here and I have a tree here, and this is my half-wave dipole antenna. We have a feed line that's going to our transceiver. And you may say, but wait a minute, there's some distance from the ground to this antenna. And is that important? Yes, it is. The distance from the ground level that you have just mounted this antenna horizontally. Now you can of course mount an antenna vertically as well. It's horizontally mounted here, but you could mount it vertically. A little more challenging to do, especially with wire antennas, but it is possible to do. But we have mounted this horizontally, and the distance from the ground is important. Why? Because depending on the distance that you mount it at, you can have losses associated with the ground, right? Or what we call reflection losses. And if you were to mount this antenna vertically, you will be introducing some additional losses associated with the ground, right? So there's in fact an advantage when you mount this type of antenna as horizontal polarization, which is what it is physically mounted. Notice this is horizontally polarized as opposed to vertically polarized. You have an advantage in that the losses associated with the ground reflection is less when it is mounted like this, horizontally. And that's an exam question. Horizontally mounted or horizontally polarized antennas have an advantage compared to vertically oriented or vertically polarized antennas in that the ground losses are less for horizontally polarized antennas. All right. So a couple more. So let's just discuss a concept, azimuth and elevation. Why it's important? Because as we talk a bit about the half-wave dipoles again, we need to be aware of the terms elevation and azimuth. So elevation is essentially up, down, or vertical, right? The vertical angle. Azimuth is the horizontal angle. So anytime you hear elevation, it's up, down. Anytime you hear azimuth, that's left to right or horizontal. Okay, so this diagram hopefully will illustrate the difference between elevation angle and azimuth. Okay. All right, so remember we said that it was important in terms of mounting this horizontally polarized dipole antenna above the ground. So the optimal distance that we need to mount this dipole antenna is about half wavelength above the ground, right? And that is just to allow the radiation or the lobes to be just right for the type of transmission that we wish to occur, right? So it's an exam question. The most optimal mounting for this half wave dipole antenna is half wavelength above the ground. Okay, so that's an exam question. So we did say that the height of this antenna above the ground is important. If it is that we were to somehow mount this horizontally polarized dipole antenna lower than half wavelength. So remember, when we talk about half wavelength, we talk about the frequency of operation, right? And the length of an antenna is dependent on the frequency of operation. So everything that we're talking about is in relation to the wavelength or the frequency of operation. So if we were to mount this antenna somehow lower than half wavelength of the frequency that we're operating on, we will affect the radiation pattern, right? And this is an exam question that the antenna height affects the horizontal or azimuthal. So you see why we talked about azimuth, the horizontal or azimuthal radiation pattern of a horizontal dipole HF antenna, such that if the antenna is less than half wavelength in height, the azimuthal pattern is almost omnidirectional. What is omnidirectional? Omnidirectional is 360 degrees all around, right? So it becomes less directional in that sense. It becomes omnidirectional. This is an exam question. Another exam question and an important point as well. What if you reduce the height of this antenna even further, much less than half wavelength, less as low as 1/10 the wavelength of the frequency, the HF frequency that you're operating? Well, if you were to do that, you actually cause the feed point impedance to decrease, right? So that's another exam question. As you mount this lower than half wavelength, you go as low as, let's say, 1/10 of the wavelength, you are actually decreasing the feed point impedance. That's another exam question. So I think that's it for the slides. Let's just, well, before we go to the question pool review, let's just mention something we mentioned last week. The two questions in the question pool were withdrawn. We dealt with them as yet, but I just thought it will be useful to, at this stage, inform all of the participants so that you can, especially if you're reading ahead or studying ahead, bear in mind these two questions. They are questions G1C08 and G1C10. Those two questions have been withdrawn, and the reason, of course, has to do with there are some changes in the FCC rules as it relates to what is called the symbol rate for amateur radio operations. That has changed. So these limitations are no longer what they were before several months ago. So we'll continue to repeat the slide so you wouldn't bother to study this or you wouldn't bother to pay attention to these two exam questions anymore because they have been withdrawn from the exam. So let us go quickly to our question pool review for all of the theory that we have covered this evening. So straight to our No Nonsense General Class License Study Guide, and we are on page 50, the end of page 53, going on to page 54. Right, so the theory we have covered today and the question pool, all of the questions are between pages 53 and 60. That's 60 for those of you that are following. All right, so let's go. Let's see if we can speed through this. All right. On what band do amateurs share channels with the unlicensed Wi-Fi service? So we dealt with this and we said that's the ISM band, Wi-Fi band, 2.4 gigahertz. Which is true of the mesh network microwave nodes? So we did discuss hams repurposing commercial equipment, Wi-Fi equipment, and creating mesh networks. And they're asking us which is true of all of these. Well, this one is correct. If one node fails, a packet may still reach its target station via an alternate route. And that's the power in a mesh network. You have different routes and different nodes that a signal or a packet or transmission can take to get to its destination. Very resilient, that mesh networking. In other words, it doesn't depend on one route only. Next question in the question pool. Which of the following provides digital voice modes? So we talked about digital modes and we went specifically into digital voice modes where we are speaking and it takes our voice and digitizes it using a codec and puts it onto one of the digital networks. And the three digital networks that we talked about or modes are DMR, D-Star, and System Fusion. Right? Those are digital voice modes. They will put the other distractor answers are also digital modes, but they're not digital voice modes. These other modes actually use a computer. In the case of DMR, D-Star, and System Fusion, you can use your voice and speak into it, right? Digital voice modes. Okay, so let's go to the next question in the question pool. Which of the following factors determine the characteristic impedance of a parallel conductor feed line? Let's dissect this question. What are they asking us? They're asking us the following factors that determine the characteristic impedance, but of what? Of parallel conductor feed lines, such as ladder line, for example, right? What determines that impedance? Well, it's two things. The distance between the centers of the conductors, that's one, as well as the radius of the conductors. So remember we showed a little sketch to show and illustrate that. So that's the correct answer. Next question in the question pool. What causes reflected power at an antenna's feed point? So what causes reflections, right? It's a difference between the feed line impedance and the feed point impedance. That is what causes that reflected power back down and cause a standing wave to develop. All right, next question in question pool. What must be done to prevent standing waves on a feed line connected to an antenna? So let's dissect this question. What are they asking us? What must be done? So they're asking us about a technique to do what? To prevent standing waves, right? That's the reflective waves coming back down on the feed line connected to antenna. Of course, the feed line is connected to antenna. It's also connected to your transmitter, your transceiver, right? But what must be done to prevent them? So to do that, remember we say hams are matchmakers. That's what we must do. The antenna feed point impedance must be matched to the characteristic impedance of the feed line. So that's matching the antenna impedance to the transmission line impedance. Hams are matchmakers. Next question in the question pool. What standing wave ratio results from connecting a 50 ohm feed line to a 200 ohm resistive load? So we worked that out mathematically. The answer was 4:1. Similar question in the next one. What standing wave ratio results from connecting a 50 ohm feed line to a 10 ohm resistive load? Again, we do our trusty calculation using our formula and we end up with a ratio of 5:1. All right, next question in the question pool. What is one reason to use an impedance matching transformer at a transmitter output? Right, so we can also restate that question, using an antenna. What is one reason to do that? Well, the reason is we want to present the desired impedance, usually 50 ohms, to the transmitter and the feed line. So that's why we'll use a matching transformer, or we could have replaced this with an antenna tuner. Okay. Next question. If the SWR on an antenna feed line is 5:1, and the matching network at the transmitter end of the feed line is adjusted to present a 1:1 SWR to the transmitter, what is the resulting SWR on the feed line? So that's a bit of a trick question. It's a kind of long-winded question, but we discussed what this means in the theory as we dealt with. So the SWR on the antenna feed line is 5:1, but we have used a matching network at the transmitter end to adjust it to 1:1. So in other words, we fool the transmitter into thinking it's 1:1. They want to know, after we have done that fooling of the transmitter using that matching network or antenna tuner, what is the resulting SWR on the feed line? Well, it hasn't changed. We did not change it. All we did was make the transmitter think it is seeing a 1:1. But the SWR on the feed line is still 5:1, and that's the answer. It has not actually changed. So that's a bit of a trick question. What is the relationship between high standing wave ratio, or SWR, and transmission line loss? So we dealt with this theory, and we said that a high SWR will increase the loss in a lossy transmission line, right? Next question. How does the attenuation of coaxial cable change with increasing frequency? So we did see that as you increase the frequency, the attenuation or the signal loss also increases. Next question. In what units is RF feed line loss usually expressed? Well, by now, we should have realized that the decibel is what we use to describe gain and losses, right? But we're talking about transmission line or feed line. So we give that in decibel per 100 feet. That's how we express feed line loss. Decibels or dBs per 100 feet. Next question. What is the effect of transmission line loss on SWR measured at the input to the line? The answer is higher losses reduces SWR measured at the input to the line. Next question in the question pool. What is the nominal characteristic impedance of window line transmission line? So we also call that ladder line in amateur radio, right? But they're calling it ladder line for the exam. They're calling it window line. And we showed the, three different types of parallel transmission lines, right? We showed the what was sometimes often called the TV line, which was 300 ohms. We showed another type, which 600 to 800, the open space. And then we showed the ladder line, which is 450 ohms characteristic impedance. All right, let's deal with a couple more questions. What's the approximate length for a half-wave dipole antenna cut for 3.550 megahertz? So we used our trusty formula, L is equal to 468 divided by frequency, and we ended up with approximately 132 feet. Right, so I'll recommend learning the formula so you can calculate for any frequency that you wish. As a ham, you may wish to construct antennas, and knowing that frequency, that formula will be very useful. Very practical formula as well. What is the approximate length for a half-wave dipole antenna cut for the 14.250 megahertz? Similar to the previous question, we use the same formula. Substitute frequency for what they gave us here, 14.250 in the denominator, and we end up with an answer approximately 33 feet. All right, next question in the question pool. How does the feed point impedance of a half-wave dipole change as the feed point impedance is moved from the center towards the end? So we showed that, normally for half-wave dipole antenna, the feed point is direct dead center, but we can actually shift the feed point left or right of that center. And when we do that, it increases the feed point impedance. That's the effect. Once you shift it from the center, it increases the impedance. Next question. Which of the following is an advantage of using horizontally polarized as opposed to a vertically polarized HF antenna? So we said the advantage of using horizontally polarized is that we have lower ground losses. We did say if we use a vertically polarized antenna, the reflective ground losses are increased, right? So an advantage of horizontally polarized antennas is lower ground losses. Next question in the question pool: what is the radiation pattern of a dipole antenna in free space in a plane containing the conductor? Let's dissect this question a little bit, right? They try to complicate what the question sounds like. So they're asking us, what is the radiation pattern of the dipole antenna? Radiation pattern in where free space in a plane containing the conductor. So all that simply means is that you have the dipole antenna mounted, and they want to know what does the radiation pattern look like. So we kind of skated over that point, but we did say it was a figure 8 at right angles to the antenna, right? So you could just review that slide and you'll see that figure 8 that we talk about. So figure 8 at right angles to the antenna. That's the radiation pattern of the dipole antenna. Next question in the question pool: how does antenna height affect the azimuthal radiation pattern of a horizontal dipole HF antenna at elevation angles higher than about 45 degrees? So let's dissect this question a little bit, right? So they try to tie us up with some terms here. Azimuthal radiation pattern, that's just the horizontal. Remember when you say it azimuthal, that's horizontal. We say elevation is vertical, but they're asking us about the azimuthal radiation pattern or the horizontal radiation pattern of the horizontal dipole. And we said that if the antenna is less than half wavelength above the ground, it is a almost omnidirectional radiation pattern. So the azimuthal pattern or the horizontal radiation pattern is almost 360 degrees or omnidirectional. All right, last question for this evening. How does the feed point impedance of a horizontal half-wave dipole antenna change as the antenna height is reduced to 1/10 wavelength above ground? So let's dissect this question. What are they asking us? They're asking us about the feed point impedance of what? Of an antenna that is a horizontal half-wave dipole. They want to know what? What about the feed point of that antenna as the antenna height is reduced? In other words, we are lowering that horizontally polarized or mounted half-wave dipole antenna, but we are lowering it to what kind of distance above the ground? 1/10 the wavelength above ground. And we said in the theory that once we start to do that, the feed point impedance will decrease as we start to reduce that vertical height or height above ground. So let's go back quickly to our slide deck. We have a couple more slides for you. Right. So again, just remember these two questions are withdrawn. The question pool that we did today were pages 53 to 60, 53 to 60 for persons who have been following. Right, and we are stuck back in this very trusty diagram that shows frequency, wavelength. It's very handy for us to bear in mind. You know, we talk about HF and VHF and UHF and whatever meter band and the actual frequencies. So we will continue to repeat this so that you have it at hand. It's a good reference point. So rather than having to look all over the place for it, we'll repeat this in the future slide packs. Should have actually done that from day one. Very, very nice to have. So folks, any questions that you have, please send to this email address or WhatsApp via the number on your screen. We do have a WhatsApp channel for anyone that's now joining and you would like to get updates, including the links to the Zoom session. We also send out additional information as well, besides information on the course. So you feel free to follow this channel. And we have a little humor for you. Again, we hope that everyone had a great Christmas, a great holiday. And this is something, again, we wouldn't go into it too much, but it's a little fun here. So please look at this at your own time for a little chuckle. And our next session will be next Friday, 5th of January, 2024, at 8:30 p.m. So I take this opportunity in advance to wish everyone Happy New Year and hope to see you in the new year. God's willing. Be safe, everyone. Take good care. Again, thank you for staying with the course. Everyone doing quite well so far. And we will see you next week. Take care, everyone.